good day to you. I'm so pleased to be here with you, looking again at Exploring Creation with Physical Science 3rd edition. And we are in the student notebook in Module 7, and we're going to try to cover the first half of the student notebook today. And we're diving right in to keep this nice and short for you. You can get on with your day after. Vocabulary word number 1 is force. What is force? It's a push or pull that acts on an object. So there we go. What is force? A push or pull acting on an object. What is the SI unit for force? The SI unit for force, basically, how do we, what term do we use to measure force? It's called newtons. Newtons are the force required to make an object with a mass of 1 kilogram accelerate at 1 meter per second squared. So here's the formula. 1 Newton equals 1 kilogram times meters per second squared, or 1 meter per second squared. All right. Sometimes we combine forces. Usually there's multiple forces going on. The net force would be how we look at all of the different forces that are acting on an object and combine them all together. So here's the net force, is the total overall forces acting on an object. So that might be a frictional force as well as gravity combined. Net force would be both of those together. All right, so they've got these fun arrows kind of to illustrate how vectors add or subtract each other depending on which direction they're going. So just like 2 + 2 = 4, we have 2 arrows that are +4 here, making a positive push of 8 right here. And then I just counted the blocks to get those numbers. And then if we have a positive force here and a negative force that's stronger, we still end up with, and we would take away this much of it. This is all very rough here, but I did try to count the blocks to make it a little closer to actual. We still end up with a negative force going the other way because this is not as great. If they're equal, there is nothing left at the end. There's no movement, there's no vector change, and they are balanced. Okay, so when an object has balanced forces acting on it, the net force equals 0. There's no change in the object's motion, like this. Okay, so let's see if I can do this and hold the phone. Let's see here. I'm gonna put you right here. See if you can see this. And balance you here on my mug. And that is me pushing with balanced force. I'm gonna turn it so I can hit it nicely. Balanced force and no movement. No movement, okay? But when an object has an unbalanced force, which I'll show you in a minute, say I'm going to make this fist so it looks like it's stronger, okay? So we've got an unbalanced force. The object accelerates. So it's going to move this way because this is going to be the stronger side that pushes. And that's what this looks like here. So when the net force is not 0, and the unbalanced force causes the object to accelerate or change position. It can move. If it had been high and low, well, it might have just I love the focus here. Might have just toppled over. You know, if it was up high and down low, it just everything that matters in this. But it causes movement when it's unbalanced. So why do they put this in here? Why do they care that we learn about balanced forces and unbalanced forces? And these are my ideas. Maybe you have some different ones. Maybe you have some better ones. My ideas were to get us to think about opposing forces and to teach us how to calculate and predict movement. There's no answers on this anywhere, so this is just my best thoughts on that. Friction. What is friction? A force that results when surfaces of objects rub against each other and pose motion. So a couple of examples would be sandpaper and brake pads on a brake disc, which I was like, oh, I know how this works. Well, I asked my husband about it, and sure enough, he had much better visual aids and ideas about this than I did. This is his rough sketch drawing. He did not know I was going to be showing you, of a tire and all the tread on it. And there is I forget what he called it on either side of it. But then on the inside, there's a disc. And inside of this disc are the brakes, and the brake inside of that you can see visually the brake pads. And when hydraulic pressure is applied to the brake pads on the brake disc, it causes the wheel that it's attached to slow down. So the friction between the brake pads and the brake disc causes the wheel to slow down. So that's how brakes on a car works. My husband's an airplane mechanic for a living, so he can tell us about airplanes, probably air friction a little bit more later too. That's something else that we talk about later. All right, why is there friction? I have some boo-boos here, evidently, because no surface is smooth. And page 229. I was like, I don't have anything in the book to look at. Yes, I do. Let's look at this. This is a really cool picture. That's why I put it on here. All right. Sorry for the motion there. All right, so here's a fancy schmancy car that when you don't have the glare from my light on it, it looks like it's really, really smooth. Look at that. Man, that looks like it's like just purely as smooth as can be. All right, well, up close, look at that. It's actually got little bits of paint chips and stuff going on that you won't feel because it's just so tiny and microscopic, right? So there's really no smooth surface at all. So friction is everywhere. Friction's affecting everything. And I had trouble with their paragraph on this on page 229. They talk a lot about the molecules, and I that's fine. There's a lot of complications with that. Again, I was discussing this with my husband, who knows science really well, and it just is easiest to explain this about regarding surfaces right now, okay, until they get into deeper stuff and want to talk to us about which molecules adhere to each other and which ones don't. We're going to just focus right now on surfaces when they nestle together. Like if these were smushed together, they would settle and ka-chink, they would just connect, right? And they would have so much friction that they would not be able to move. And it's because they were able to nestle into each other like that. But if you had two surfaces that were not able to nestle in each other like that, they would have low friction. They could still move across each other. Those two surfaces would not connect like that. And so that is right there. We have the box. The surface of the box and the surface right here, and there's friction between the two of them. And saying it's really hard to pull this. And then we also have gravity pushing down on the box, making it heavy. So we've got net forces going on. Okay, whether it's somebody pushing here, or the friction on the ground, and the gravity, lots of stuff going on. So let's look at static friction. Static friction is friction that opposes the initiation of motion. So you can't move it to begin with. So static friction is just stuck, okay? Static friction is stuck. Kinetic friction, friction that opposes motion once the motion is already started. So it stops something that's already moving. I think of like a train already going down the tracks, and they put on the brakes. So that would be a kinetic friction. Okay, so move over here. We're on page 187 in our student notebook. We've got different types of friction. So we'll start with sliding friction or kinetic friction, or also called dynamic friction. So this is like sledding or ice skating. It just slip and slides right there, sliding down a hill or sliding down a slide. It doesn't have to be downwards. It can just be across too. All right, rolling friction, or I said or roly-poly friction because they have this also known as, and there's no thing in the book about what it's also called. I think that was this one over here. Again, a few typos in this book, but it's kind of fun to find them. It's like Easter, you gotta like find the eggs and find the errors in the book. All right, so using a dolly or a wheelchair would be rolling friction. All right, number 3, fluid friction. It is early here. Fluid friction are always liquids and gases. They're considered fluids. And good morning, Phoebe. You can go on through. I'll come see you in a minute. So like they said, like stirring any kind of batter that's somewhat liquidy would be the friction you're feeling in fluid friction. So that's what that is. And air resistance would be just, you don't think of any resistance going through the air. However, what you're wearing and how the airplane is shaped it does make a difference on your air resistance. And so when you need an aerodynamic helmet or clothing, that's to reduce air resistance so you can get through the air without having resistance. Think of an umbrella. This is a thought that just came to mind. An umbrella that is turned into the wind. You have it going smoothly around the curve of it. But as soon as you flip it around, it's catching all the wind. It almost wants to pull you with it. And that's air resistance. And so it's more aerodynamic to be turned into the wind so it can go curve around the umbrella. But the other way is catching it all, and it's like acting like a parachute. So another air resistance example there is a parachute. All right, I'm on a roll. All right, explain how a force acting on an object affects the object's motion. Oh, well, this is where you get to hear Mrs. Wigton sing. Oh, I love it. All right, so here we go. At our CC campus, this is something we have little songs for everything. So, an object at rest tends to remain at rest, and an object in motion tends to continue moving in a straight line at a constant speed unless an outside force acts upon it. Newton's first law of motion. All right, we could just go on all day. I just like to sing the song. It's really fun. All right, so that is how a force acting on an object affects the object's motion. I couldn't say it any better than that right there. So that was my answer for that. What is the net force of a pair of balanced forces? Oh, it's one of those trick questions again. Nothing. It's nothing. So that is the answer to 7.2. All right, I got artsy on this one. All right, how are the 4 types of friction different, and how are they similar, and what do they do? Okay, so here we have, see if I can get this all in here. In the blue, you have static friction is strongest, and then sliding friction is next strongest, and then rolling friction. That is not going to roll really well because that friction's too flat there. But so static is strongest, sliding is next, and then rolling friction is next. And all of these 3 affect solids. Okay, and then over here we have fluid friction, which is liquids and gases, and air resistance, which is also a fluid friction too, because it's gas, right? And then all of these are forces that oppose motion. So there's the whole picture, best I can. All of those oppose motion, or their forces. So say, may the force be with you, you're going to have to ask, okay, do you mean, which kind of force do you mean? So, all right, bad joke, Mrs. Wigton. All right, so here we go. Gravity. What does gravity do in order to make a dropped object begin to move? Well, it causes an unbalanced force, like we saw earlier, where we had a stronger side and a weaker side, and it gives the object constant acceleration, which is change, right? Constant change. So, so if we are dropping this, or we just let go of this vase in the air, obviously force of gravity is greater than any other. There's no gravity that goes any other direction. It always goes towards the earth, so down for us, and it would cause it to fall to the ground and probably break, depending on what's down there. So unbalanced force is gravity coming down on objects, pushing them towards the earth. What is free fall? Free fall is falling towards the earth with nothing in the way. So they don't hit the ground like up here and stop. Well, maybe you do. But for a little while, this was in free fall, right? If we dropped it from more than a few inches, it's in free fall for a short time. Maybe this person jumped out of an airplane. Where is your parachute, lady? All right, so what's wrong with your legs? Anyways, so yeah, free fall is just falling towards the earth using gravity and with nothing stopping it for a while, right? Eventually something always stops whatever's falling because you're going towards the earth. All right, so what is the important sentence on page 234? It is this. You don't even have to go there to see it. You're welcome. It is the acceleration due to gravity for any object is this amount. So here is the secret to gravity. You need to know the secret code here. 9.8 meters per second squared in metric, or 32 feet per second squared in English units, or imperial units is another way to put that. I had a huge conversation with my husband about this as well, because I was like, why? Is that Maisie? Is that Maisie? Hello? Oh, there she goes. Because I said, well, I grew up in England for 5 years, and in British school, we used metric system for everything. But he says, no, alas, even though they use meters for a lot of things, they use imperial, oh, sorry, I gotta shut the door, gallons. I said, but they use liters. I'm almost positive, but anyways, it's these are most of the world. He said it's changing in England, and here's why: is because most of the world used metric system, and England had its own imperial system, which sounds very British. And then it was part of the European Union, kind of. And so it was going to the way of the metric system. And now we have Brexit, and they're leaving that, and they're going back again. So it's all in flux there. But they still are not like using they never use feet. I've been there. They don't use feet. All right. So what is the equation? No, you've got any outies, Izzy. You've got any outies, and you cannot just go in and out and in and out. So you have to decide, which are you going to do? All right. If I let you through, you're stuck. You're stuck. Go on. Oh, see, she had any outs. She just want to know if she could do it. This silly girl. All right. So what is the equation for determining how far an object will fall under the influence of gravity? Well, here's the distance. Oops, sorry, bumped the phone. Distance equals half times, oh no, acceleration. I was like, what's the A stand for? Acceleration times time squared. Okay, so that is, and here's the acceleration amount. It just depends on whether you're calculating in, go down here, in the metric or the imperial system right there. All right, so that's how you determine what A is, and when you're doing a free fall, basically measurement with just gravity as the only force. Okay, so that's what we're going to do a little bit of right now. So here's an example of a woman who dropped a rock from a bridge into a river. Boo! It took 1.2 seconds to get down, and 9.8 meters per second. Oh, look at that, 9.8 meters per second. That's where they got that. And how far in meters was that? So we got to stick to the meters and seconds. Make sure all of our things match, or else we're doomed. All right, Maisie, out. Goodness sakes. All right. So here we go. We're going to plug it all in. We got our half. We got our 9.8 from the A for acceleration. And we got our 1.2 seconds. We're squaring it right here. Squaring just means timesing it by itself. And why did we cross out all these S's? Because we got second squared here, and we got S times S here, which means second squared again. So we're going to eliminate both of those. So we've got meters only. And so we can determine the distance in meters, and that was 7.056 meters. Woohoo! We figured it out. All right, here's another one. A stone is dropped from the roof of a house. A person standing on the ground watches and times the fall of the stone with a stopwatch. If the stone takes 1.1 seconds to fall, how tall is the house, using feet this time as your measurement? Okay, so this time acceleration is going to have to be the 32 feet per second squared, because that's the imperial measurement for it. We've got our time. What is the distance? Well, here's the formula we're going to use, and let's plug it in. Sometimes it's easier to work in decimals instead of fractions. So we're going to convert that half to 0.5, which is half of a whole in decimal. We're going to bring down our acceleration amount here and our time, square it. And when you punch it all in, this is what you get at the end, 19.36 feet. So not too shabby right there. All right, last section we're going to work on today. It's the you do science. My son helped me as I dropped an eraser from the top of the ceiling to the ground, and he kept the times here. And actually they wanted us to make a graph, so made a graph here of our results, and we got nothing readable, legible, consistent. I mean, I don't even know what happened here. We did it though. We did what it said. All right, so I do not understand the results of that. So inertia. The tendency of an object to resist change in its velocity. So inertia says, I'm on a roll, no change, please. So it's moving, and it doesn't want to stop. It doesn't want to change its direction or speed. So that's inertia, okay? And we got lots of we go deep dive into inertia in the next section of this. But we're going to just do a little bit of history. Here's good old Aristotle. Aristotle believed that there were separate rules for the heavens and rules for the earth. And in the heavens, everything moves in circles, he said. Like the earth around the sun and the moon around the earth. And for the earth, well, things are just normally at rest unless something makes it move. So naturally, things just like to rest. He had no experiments. He just had theories and beliefs. Philosophies. All right. Galileo, Galileo, here we go. Galileo studied inertia, and he used experiments like he created a skateboard ramp that was really tiny, and he put things on it that would roll, and he studied inertia that way. You can study inertia by skateboarding on a half pipe. Let's see here, an object at rest. Oh, I feel a song coming on. This is another one of those, but actually Newton was the one who kind of finished this law. So an object at rest tends to stay at rest, right? An object in motion, he believed, would stay in motion forever unless it's stopped by a force, which is pretty insightful of him because he didn't even know about friction or gravity. So this is a brilliant man. He believed that objects could theoretically stay in motion for forever, which is not possible here on Earth. But yeah, theoretically, and in a perfect world with no friction or gravity, yes, he's right. No other forces. Newton. All right, Mr. Newton developed laws of motion. This guy was amazing. He defined the law of gravity. He proved that white light is just really lots and lots and lots of colors by using a prism. And he developed calculus in just a matter of months. That guy, he was just astounding. So we're going to deep dive into his laws of motion in the next section. And thank you so much for joining me today. I hope you have a wonderful, wonderful rest of your day. Take care. Bye-bye.